For star formation, we're going to start off talking about nebulas. And a nebula is basically a cloud out in the galaxy. And the cloud is going to be filled with mostly gas, hydrogen and helium gas, and also a little bit of dust. So think of carbon molecules. And most of the nebulas in our Milky Way galaxy are in the disk. Here's a picture of a gorgeous nebula. But for star formation, we're going to want a very specific type of nebula. So molecular clouds are a subset of nebula, and molecular clouds are going to be cold, and you want them to be cold because then they have less gas pressure. The molecules aren't bouncing around as much. And when the molecules aren't bouncing around as much, that would let gravity more easily pull them together. Molecular clouds are also more dense than the typical nebula, and more dense is going to help us form stars because more mass means more gravity. So in this nebula here on the left, you can already see that there's this dense region that's already being pulled together, and new stars have already formed. There's one, right? There's one up here. So these nebulas can be a little tricky to find if you're looking in the visible light, because nebulas, especially cold nebulas, tend to be dark. But if you switch to a different color of light, like maybe radio light, they will glow. Infrared light is kind of fun with molecular clouds, depending on the type of infrared light that you're looking at, what specific wavelength. You might be able to see right through the cloud like it wasn't even there. You might be able to see the stars that are forming inside the cloud, or you might not be able to see through it at all. So infrared is really wavelength dependent. So you have these nebulas out in the universe. Here's a nebula, molecular cloud, because it's cold. And these nebulas seem to be fairly stable. They're not going to randomly just collapse on their own. So in order for them to collapse, in order for the gravity to become stronger than gas pressure, which is supporting it right now, it is probably going to need to be shocked. So maybe a nearby star will explode as it ends its life, and it sends out a shock wave, and the shock wave will squeeze the front side of that cloud a little bit, making the cloud a little bit more dense. And now all of a sudden gravity is stronger than thermal pressure, and now it might be able to collapse under its own weight. And once it collapses enough, it'll start forming stars. So one of the things we have to worry about is as a gas contracts, it heats up just through conservation of energy. And so while this gas is collapsing and gravity is trying to form stars, the cloud is fighting back. The cloud is heating up because of the collapse, and that's going to try to slow gravity down, try to slow the collapse. So depending on the balance between the gravity and the pressure, depending on how it works for this one nebula, that affects how many stars it'll make. It'll affect the masses of the stars. So here we have a computer simulation of a molecular cloud. The color indicates density. So let's let gravity try to collapse this cloud. As it fragments pretty quickly, the turbulence will just fragment it. And if there was no gas pressure supporting this, it would have been able to all just go down into one big star at the very center. But because there is that gas pressure supporting it, it broke it up into pieces, and it's going to continue to try to fragment into those little pieces. Zooming in, look at one little knot of material that was able to get denser than the rest. It's going to be the first part of the nebula that's going to be able to form stars. Now there's several places in the nebula that can form stars. Quite chaotic. So what we're doing now is forming an open cluster of stars. Open clusters of stars are stars that were all recently made in the same area in the galaxy. And this is why stars form in clusters. This video is very sped up if you watch this time up here. Zoom out to see the whole cluster. If you were to come back in several million years, these stars will eventually drift apart. They will not stay together forever. So when your gas is getting collapsed by gravity, it heats up. And once it gets so warm, it's going to try to cool itself off. It's going to radiate light to try to cool. And if your nebula has some molecules in there or some rare elements, that makes it easier for it to radiate specific frequencies of light that will be able to escape out of the nebula, and that will carry away the energy and cool the nebula, and that will allow it to fragment more. So if your nebula is allowed to cool itself while it's contracting, it's allowed to fragment. And that's what we see today in the galaxy. Molecular clouds today have molecules in them, like carbon monoxide, water, right? But when we go back and look at the first stars, the very, very, very first stars formed out of the only ingredients that were available, just hydrogen and helium. And hydrogen and helium can only emit lines for hydrogen and helium, but that means that those lines will get reabsorbed by all of the other hydrogen and helium in the nebula. So the very first stars could not cool themselves very effectively, and that would not let them fragment. So the very first stars would have formed monolithically. You would have had one big cloud, one big knot, collapse, and just form only one star instead of forming several stars. So the very, very, very first stars were huge. We can't see any of them today. They all died. Massive stars don't live very long. But all the evidence that we have, including the fact that they're all gone, tells us that they lived brief lives because they formed slightly differently, because they couldn't cool as the nebula was contracting. This image that I got was the best image I could find to illustrate this topic, but it's kind of funny. This is actually illustrating something else about star formation. This was from a supercomputer model that was trying to see what dark matter annihilation had any effect on heating the nebulas when the first stars were forming. And what they found was if they added dark matter annihilation into the star formation process, it would actually heat it up more. And when you included that extra heat, it was not able to fragment as much. So while this picture isn't related, it also is related, but it was the best one I could find. All right, so you've got your knot of material that has been collapsing in that nebula. Now let's just zoom in and look at one of those stars that was forming, because it's not done yet. That one chunk of material, that one fragment, still has several steps to go. So that one chunk is going to undergo a few processes. Its rotation is going to increase. All right, remember that's the conservation of angular momentum. The ice skater, pull your hands in, you speed up. It's also going to heat up just because of the fact that the gas is getting compressed, and that's still continuing on. This thing is still shrinking under gravity. That extra heat is going to try to get radiated away. But while it's there, it is going to slow down gravity a little bit. It's not going to be able to collapse as fast. And because of the particles all bumping into each other time and time and time again, eventually the particles will either get pulled into the center of the sun or end up in fairly stable orbits in the disk. So that's just a consequence of gravity and the gas molecules always bumping into each other. Your cloud is going to flatten into a disk. When you're here, and your protostar is forming, so you've got this huge chunk of hot spinning material down there, right? It's going to get a really strong magnetic field. So your protostar gets a strong magnetic field. And magnetic fields reach out and can affect the disk around it. And so while this protostar, is spinning, it's trying to spin its magnetic field with it. But that magnetic field on the outside drags through the disk. And so one effect of that is some of the star's spin, some of the star's angular momentum, gets transferred to the disk. And so the star actually loses some rotation by giving it to the disk. The magnetic fields are also thought to help particles escape the really hot protostar as it's forming. And so we would call that protostellar wind. Here, protostellar wind is basically charged particles escaping from the forming star, just like the solar wind for our sun. This is the protostellar wind. All right. Protostellar winds are pretty intense. A lot of particles do get to escape. And the magnetic field does one more thing, which is odd but interesting. Some of that protostellar wind gets directed into jets, and they pop out of the rotation axis of the system. And so these forming systems shoot out jets of material. So while most of it's collapsing down, getting tighter and tighter by gravity, some of the material gets to escape. It gets enough energy to escape gravity, gets shot out of the system, out these jets. The star is going to keep growing, getting more massive and trying to collapse further. But eventually the star is going to give off enough energy that it's going to blow away the remaining amount of gas in the disk. So between the protostellar wind and the jets, the gas in the disk will eventually get blown away. It'll be redispersed back into space. Not only is that going to stop the star from getting any more mass, it's also going to stop any planet formation that was going on in the disk as well. So while you're looking at the star here, think also that there's probably planets forming in this disk at the same time. Here's a picture, albeit not the greatest picture, but there's a forming star right down in here. We're looking at the disk edge on, so like at the edge of a record. Here it is. You can see some of the new starlight peeking out above the disk and below the disk. And you can see a jet of material shooting out one pole and shooting out the other pole. So this is observationally backed up. We do see disks around stars. So how does the star formation look on an HR diagram? So we're going to start off over here, really dim and really cold. So that's why we're off the figure. Really dim and really cold. Okay. And for it to be able to go and become a main sequence star, it takes a certain amount of time, and low mass stars take longer. They have less intense gravity. So it might take them 150 million years to form and become a star in the main sequence. High mass stars, just a mere 60,000 years. Which, do you remember when we talked about open clusters? I said all these stars were formed at the same time. Not perfectly the same time. The high mass stars would have formed first. The low mass stars form a little bit later. But roughly, in astronomical terms, that's still pretty close to the same time when you're talking about a cluster of stars. So in stage 1, the protostar is basically forming. And as it forms, it's going to heat up a little bit. What heat it does have, it's going to try to get rid of through convection. And then once it gets to the surface and radiate away the light. Right? So it's getting a little bit more luminous as well as it's trying to radiate away that energy. So it's moving up on the figure. And because of the collapse, it's getting hotter, so it's moving left on the figure. In stage 2, the surface temperature stays the same. So that's why we're not going to really move left or right on the graph here for stage 2. Gravity is going to be able to just shrink the protostar without really affecting the surface temperature. And so it moves down on the graph. Even though the surface temperature stayed the same, and the amount of light coming out of the star per unit area stayed the same, because the star got smaller, it lost surface area, so it actually gets dimmer. And that's why it moves down right here. For stage 3, the protostar surface heats up, so it's going to move left on the figure. This is when fusion starts, and the balance of energy in the star is changing a little bit, so how the star is trying to move energy through its mass, through its bulk, is going to change. Instead of convection trying to get the energy from the inside of the protostar to the surface, is going to switch over to radiation, so the random walk of light, trying to get the energy to the surface. And that change happens because of the changing temperatures and densities. So fusion is started here at step 3, but it's not enough yet to stop gravitational collapse. So by step 4, the star will eventually collapse and the core will heat up a bit more. And by the time you hit step 4, fusion rates have increased enough to completely stop gravitational collapse. And now it's stable. And the solar thermostat is going to be active, keeping it stable. And at step 4, we say star formation is done. You have a main sequence star. Good job, star. Okay. It only took you 150 million years.